Let us discuss the notion of uniform continuity. So what does uniform continuity mean? To understand that, we need first to recall what was the definition of continuity at the point. Okay, so if we have two metric spaces, x and y, and a continuous function between them, a continuous function at the point P, the definition is that for every epsilon bigger than 0, there exists some delta such that if the distance between P and Q is less than delta, then the distance in Y between f of x, and let me continue in the next line. Then the distance in Y between f of P and f of Q is less than epsilon. Now, from here, we defined f of x to y continuous in a set E containing x. That meant it was the same definition. Okay, we could copy paste. But now this definition needs to hold for every point P in E. Okay, so let's that's the key difference. So we have continuity at a point and we have continuity on a set, in a set. Now here, there is a small detail that sometimes it's easy to overlook. That is about the existence of delta. Okay, this delta depends on, of course, it depends on epsilon, but also on P. Okay, so that is what the uniform continuity is all about. Let me explain. Let me explain with a picture. Let's say, just to keep things simple, let's work with real functions. And let's take the function x squared. Now for this function, let me just graph it. It would look something like this. Okay. And here, what is the definition saying? The definition is saying that if the distance between P and Q is less than delta, then the distance between the images is less than epsilon. So that means that if we fix epsilon, let's use a different color. Let's say this is our epsilon. Okay. And we have the 2 points f of P and f of Q within epsilon of each other. We can somehow send that back to the pre-image, and what we get is that P and Q are within a distance of delta. Okay, so we have our PQ in this tiny space. But we can take the same, exactly the same epsilon, and we could place it somewhere else. Let's say here. Let's use a different color. And just do the same and see what happens now. Now we could take f of p, f of q, and when we translate them back, so we have our p and q here, but now the delta can be much bigger than before. Okay, so you see that the what is happening with this function as we take the same epsilon, but we take it higher on the y-axis, then what is happening to the corresponding delta is that it's getting smaller. Okay, so somehow what we see here is that delta gets smaller as p gets larger. Okay. Actually, we can make a computation to show that delta goes to 0 with p. It's very easy. So here what we do is f of p minus, well, let's call them, yeah, like this. This is p squared minus q squared, which is p plus q times absolute value of p minus q. Okay, and here notice what we want to do here is to estimate this part by epsilon, right? But we don't just go ahead and say that. We are going to find epsilon along the way, okay? So here the info we have is that p minus q in absolute value is less than delta, and we want to show that that implies that this fp minus fq is less than epsilon. So let's get to it. This is less or equal. Here what we are going to do is to apply the triangle inequality. Okay, and we can just go ahead and say, well, p plus q is the absolute value. Well, let's write it carefully first. This is 2p plus q minus p, okay, times p minus q, and that now by the triangular inequality, that is 2 times p plus q minus p times absolute value of p minus q. Okay, here this p minus q, I can just write it, sorry, q minus p, I can write it p minus q. And here, notice what happens. This is less than delta, this is less than delta. So this is 2 times p plus delta times delta. Okay, and here we are almost set, okay, because this is already telling you what I was saying, that the delta it's going to complicate your life, okay? So how do we show that? Well, actually, because we are interested in small delta, we can assume that delta is less than 1. So this is less than 2p plus 1 times delta. And now if we want this to be less than epsilon, that means that our delta has to be less than epsilon divided by 2p plus 1. Clearly, delta depends on epsilon and p, but here what we see is that as p tends to infinity, delta has to go to 0 because p is dividing. Okay, so this is what I proved before with the picture. The idea of a uniformly continuous function is precisely to avoid this problem, to avoid that delta becomes smaller depending on the point, okay? So the definition, the precise definition is basically the same one we had for continuity, but it's emphasized that there exists some delta. For every epsilon, there exists some delta, such that the distance between Fp and Fq is less than epsilon for all P and Q in X for which the distance between P and Q is less than delta. Notice that what we did before was to somehow fix P and then move the Q's around P, and then delta depended on P implicitly, but we didn't emphasize that. Now, here there is one delta, okay, and then somehow that delta has to work for every pair PQ that we choose in X. That's the difficulty. That's the key point. And actually, you may be wondering, an easy remark is that if F is uniformly continuous, then F is continuous. Okay, so being uniformly continuous is more restrictive. It's a better property than just continuity. Okay, so the example that I just shown is not uniformly continuous. Okay, because we are taking 0 infinity. Okay, but if we look closely to it, to the expression that we got here, okay, in zero infinity is not uniformly continuous, okay, because this number delta goes to 0 as P becomes large, but it is if we work in some closed interval AB. Okay, why is that? Because then this number epsilon divided by 2p plus 1 is bigger or equal than the largest number we can put in the denominator. Okay, so here we can put epsilon divided by 2b plus 1. Okay, and then as long as delta is less than this number, we are good. And this definitely works for every pair P and Q. Okay, as long as both PQ are in A, B. So what I'm trying to say here is that uniform continuity depends on the function, but it also depends on where we are working. Okay, and actually, if you noticed, here AB is a closed interval. I did that on purpose because closed intervals in R, they are compact sets. And actually, that is the important property. For example, we could take 1 over x in 0 infinity, okay? And here, what we see is it's a similar type of problem, okay? Because we have here our 1 over x, all right? And then, just as before, we can fix epsilon. Okay, and try two different heights. So this case will give us a reasonably large delta. But if we try the other one, this one a little higher, look what happens. Actually, it's going to be much smaller, and it gets smaller the closer I get to 0. Okay, so in this case, delta tends to 0 as p tends to 0. Okay, it's a similar type of computation. I'm not going to do the details in this case, but what I want to emphasize is, well, actually I wrote 0 infinity, but it could be 0 1, let's say, because here cutting off here, it's not going to really become a problem. Okay, because the farther we go towards the right, the larger the deltas become. Okay, or if you want, the lower we put this epsilon, the larger the delta becomes. Okay, so what is happening here? Notice what is happening here. F of x is continuous in the interval 0, 1 open on the left. Okay, but is not uniformly continuous. And here this again emphasizes the theorem. Okay, the theorem is going to say that we need a continuous function in a compact set. Okay, that will guarantee uniform continuity. So here I have given two examples, one where the function was very good, perfectly, it was a polynomial, but we didn't have a bounded set, so the set was not compact because we were in R. And in this case, what fails is that the set is not closed. Remember that Heim-Borel theorem in R says compact if and only if closed and bound. So what is the theorem then? The theorem says that whenever we have a continuous mapping from a compact metric space into another metric space, then we know for sure that that mapping is uniformly continuous. Let's prove the theorem. So here we have two hypotheses, one that X is compact, the other one that F is continuous, and we need to use both. Okay. So somehow what we need to show is that the delta in the definition of continuity is independent of the point. So that is what we are going to do. Okay, so first thing, because this is a continuity proof, let epsilon be given, because for every epsilon. And then what we know from the continuity of F okay, we know that for every p in X, there exists some number delta such that if the distance between P and Q is less than delta, and this would be a distance in X, then the distance between f of p and f of q would be less than epsilon. Okay. But here we need to make a small adjustment because, of course, this delta here depends on the point where I'm working. So what I'm going to do, I'm going to just make that very explicit so there is no confusion about it. And instead of delta, what I'm going to write is phi of p, so that it's clear that this is a function of p. Okay. So this is what we usually call delta. Okay, and then there is one more adjustment that I'm going to make right now, just to make our life easier later. Instead of epsilon, I'm going to take epsilon halves. Okay, this I can also do, and it will, this is the type of thing that you realize when you finish the proof. It's like, oh, I should have taken epsilon half, then I will get epsilon here. Up to you. But because I already know, I will just go ahead and do it. Okay. So notice what happens here. This is for every point. Okay. So then if we have our function and we have our point P, right? It's the same picture we had before. So we have our epsilon here, and then that gives us some neighborhood of P. Okay. So that neighborhood, I'm going to call it J of P. J of P. Sorry about that. So we are going to define J of P as the set of all Q in X such that the distance between P and Q in X is less than phi P over 2. Okay. So these are just, for example, it would be this neighborhood. These are just small neighborhoods around each point P. The neighborhood where the definition of continuity, where we are guaranteed that the definition of continuity works. Okay, so then what is going to happen, let's move this over here, is that for different points, I'm going to find different neighborhoods. Okay, so for example, if this is some P2, okay. So I'm going to find a different neighborhood. I was a little too fast there. There we go. Which is going to have a different size. Okay, depending on where we are working. But you get the idea. So now what is going to happen is that the JP for P in X form an open cover of X. Okay, because for every point in X, we have one of these. Okay, and all of them together, they are a collection of neighborhoods and they cover the whole of X. But guess what? Here is where we are going to use that X is compact. Okay. And here we have already used our two hypotheses. The compactness is going to tell that there is a finite subcover Okay, but because the cover is indexed using the points, that means there exist points P1, P2, let's say Pn, okay, such that X is contained in the union of the corresponding neighborhoods. JP1 union JP2, and so on all the way until the last one. Okay. And here comes the big trick, okay? Because we have finally many of them, we can take our delta, okay? Finally the delta appears. Remember, there exists some delta, so somehow we need to find it. We're going to take 1/2 of the minimum of these phi of P1, phi of P2, all the way phi to Pn, okay? Here, notice what happens. We know that delta is strictly positive, okay? And this happens because we have a minimum of n positive quantities. But here, for example, in that example we did of the function x squared in the whole 0 infinity, for that one we would have a problem because the infimum of an infinite number of positive quantities could be 0. That is exactly what was happening to us. Remember that delta would go to 0? When I was taking the whole 0 to infinity, delta was going to 0, but then as soon as I limited the interval where we were working to some compact set AB, something that was bounded, then things were fine. The delta then would be strictly positive. So that is what this step of the proof is reflecting. So now we are ready to finish the proof. So here, now let PQ in X, okay, because that's what we need from the definition, and let them be such that the distance between them is less than delta. Okay, this is what we have in the definition. Delta, the one we just defined. Now, what we know for sure, we have here our P and Q. What we know for sure is that this P is going to be within some, within the reach of some J of Pm. Okay, so there is some Pm such that P belongs to that neighborhood. So, because it's a covering. So then P belongs to J of Pm for some Pm of the ones that we selected for the subcover. And here comes the important thing. So by definition, the distance between P and Pm is going to be less than 1/2 of phi of Pm. Okay, but also the distance between Q and Pm is less or equal, now triangular inequality. Okay, we are going to use this and this, okay? Distance from P to Q plus the distance between P and Pm. Okay, and this is less than delta plus 1/2 of phi of pm, and that the whole thing is less or equal than phi of pm. Okay, this is the reason why we took half of the phi. Okay, so that here we could, I did a similar thing in the example. Remember that I said, well, delta should be, it's small, so then we can estimate by the half. Okay, but in this case, the delta is the minimum of all of them, so we can estimate by less or equal than 1/2 of phi of pm. Okay, but then by continuity, remember in the very beginning, here, in the very beginning, we said that for every epsilon, there existed some phi such that, and here comes the important thing, if the distance between P and Q was less than phi of Pm, then the distance between the images would be less than epsilon halves. And that means the distance between Q and Pm, which is because the distance is less or equal than phi of Pm, then the distance between f of Pm and f of Q is less than epsilon halves. And from here, again, by the triangular inequality, I take f of P, f of Q. This is less or equal than the distance f of Pm to f of Q plus the distance between, between f of P and f of Pm, which is epsilon halves plus epsilon halves, and that is the epsilon that I mentioned in the very beginning. That's the reason why we took epsilon halves.